There we go. So we finished 2.4 the other day. What we're going to do today is we're going to run through, I kind of hope to finish it, but we'll see what happens. It's an introduction to 2.1 and 2.6. So it's an introduction. We kind of have to get some definitions under our belt before we can continue, because some of the other sections refer to some of the definitions in these two sections. But then at the end of the semester, if we have enough time, we're going to come back to the idea of graphs and graph theory a little bit and get a bit more in depth into it. So this kind of two sections compiled into one is just an introduction to some of the more basic definitions. And then later we'll come back and we'll touch on it in a bit more detail. It's just that we need some of them, these, definitions before we can move on to chapter 3, which will be next. So here we go. So we're going to introduce the idea of something called graph. Now, it's not the graphs that you are used to, not like, just graphing the parabola x squared or something like that. Like I said, we're going to focus on basic terminology and these things called trees. And then we're going to kind of return to these ideas as we need them. So first definition is what a graph is. So a graph in this context is a diagram of dots, which we're going to call vertices, that are connected to lines or curves, they don't have to be straight lines, called edges. So we're essentially just going to have a bunch of dots and a bunch of lines that can be curved, connecting these dots together. So I need to scroll down a bunch, but I'll wait a second so people can get that down if they're writing it down. But the first example is kind of large, so. Okay, so I gotta scroll down a bunch. I think I even need to zoom out a little bit. Yep. Well, let's stay zoomed in for a second, and then we'll zoom back out. So, I missed this little tiny piece up here. Scroll the tiniest bit back up. There we go. So the edges are going to show some type of relationship between the vertices, between the dots. Sometimes that relationship has context, and sometimes it's just that those two are connected. So say we have this map of part of USC's campus, and we're going to use a couple things. So let me get some colors up in here. So we're going to use LeConte, which is over here. We're going to use different color. We're going to use the National Advocacy Center, which is over here. That's a little hard to see, but the colors aren't really that necessary, but just keep track of things. Let's make that a darker green. We're going to look at Russell House, which is down here. Just trying to point them out on the map because we're going to need them. Wardlaw, wherever the heck you say, I don't even know. Okay. And the War Memorial, which is, where's that? There it is. Up in this corner, really tiny. And then one more, what other color can I use? Bright pink, I guess. William Bryce Nursing, which is over here. All right, so essentially what we're gonna do, so now I need to zoom out a little bit. Is I want to draw a graph to kind of represent these 6 buildings, and we're going to draw edges between the vertices if there's a road that connects the two buildings, and just like one road, you won't have to like turn, make an official turn to get to the building. So the first thing I'm going to do is I'm going to write down all the vertices. I need to zoom out a little more. So we're going to take all of the buildings that we're talking about to be our vertices, and I can put them in whatever order I want. So let's kind of put them in a semi-order that they appear. So, the National Advocacy Center is kind of up here. Whoops, can't spell. And then let's do Williams Bryce. And then LeConte. The order does not matter. The placement of these things doesn't matter. I'm just trying to put them semi in kind of the order that they appear on the map. Russell House, Wardlaw, and the War Memorial. So I've essentially made all of those buildings into my vertices of the graph. So all of those dots are just my vertices. In this case, they have some kind of context to them. You don't always need context for a graph, but here we do. So now I want to draw edges between these vertices if there's a road between those two buildings, and just one, no turns. You can, get down to a street, walk straight across, and be at the other building. So let's start with Ward law. So now we're going to be a bit how do I want to phrase this? So you're going to walk out of this building and go to a street. And once you hit that street, that is the street you have to walk on. So essentially, if I leave Ward law, I could go out this way and I could walk straight across and I'd hit Russell House, right? So essentially, there's a street between Ward law and Russell House. So I'm going to, and it zoomed in a little bit on me. So I'm going to draw an edge between those two. But also, if I walk out of Ward law, but instead of walking down to that street, if I walk out this way, so I go over to this street, and then I walk directly up, I can hit the War Memorial. So we're going to consider those two to be related as well. So essentially think of, you can walk out of the building and get to a street that's nearby, and then just walk down that street. And if you can walk down that street without having to make any extra turns, then we're considering those two to be related. And then there's no other, nope, that's a lie. If I go back out to this street again, the street that I took to get to Russell House, but I go past Russell House, I can also hit LeConte. So this is also going to be related to, whoop, LeConte's down there. This is different than my notes. Gotta be careful. And if I continue down that road just the tiniest bit more, I would have also hit Williams-Brice. So Ward law is also connected to Williams-Brice. I probably should have started with a different one. That's the one that's connected to the most, I think. And those are the only places we can go. So we can't get to the National Advocacy Center by just one road. We would have to take a turn from Ward law. So those two, there's no edge between Ward law and the National Advocacy Center. But now let's kind of go clockwise, if you will, and hit the War Memorial. So the War Memorial, well, we already know that it's connected to Ward law, so we don't need to worry about that. But what else can we get to? Can't get to Russell House, we'd have to make a turn. Can't get to LeConte, can't get to Williams-Brice. But, and now it might be, if I scroll up just the tiniest bit, just the tiny, hello, scroll up the tiniest bit, thank you. We do have kind of this street right above it. And if I go completely down that street, I would hit the National Advocacy Center. So I do have an edge between the War Memorial and the National Advocacy Center. And that's the only other one that the War Memorial has an edge to. Now, what about the National Advocacy Center? Is there anything else I can get to? Well, if I kind of walk out onto this road here and go down, I could hit either LeConte or Williams-Brice. So I can get to Williams-Brice or LeConte from the National Advocacy Center. Whoops, I got rid of the color. Didn't mean to do that. What about Williams-Brice? Is there anything else that I can get to from there? Well, if I go down the street this way, I can either hit LeConte or Russell House. And if I kept going, I could hit Ward law, but we already had that one. So Williams-Brice also connects to LeConte and Russell House. What about LeConte? Oh, man. Well, LeConte, we already have a pretty decent amount that's already connected to LeConte. So is there anything else that LeConte can get to? Well, the only places that LeConte doesn't already have an edge to is the War Memorial or Russell House. And the only one that we can get to from LeConte is if we were to come out of LeConte this way and walk over to the Russell House to the left. So it is connected to the Russell House, but not connected to the War Memorial. Technically, you'd want to triple check that Russell House can't connect to anything else, but since it's kind of the last one we have, it should already be taken care of in all of its options. So Russell House can connect to Wardlaw. We've already got our edge there. Can connect to LeConte. Already has its edge there. Can connect to Williams-Brice. Already has its edge there. Can't connect to either of the other two. So this would be a graph on those buildings with edges between them if we can get from one of the buildings to the other, essentially just with one straight road without having to make any turns. So this would be a graph. Hopefully that makes sense. One thing I'll note quickly, because I'm thinking about this is what I might do for your quiz. So on this particular graph, there's 1, 2, 3, 4, 5, 6 vertices, because we had the 6 buildings we were talking about. And if we start talking about how many edges we have, well, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we had 10 edges. Just to note them. So this would be a graph on 6 vertices and 10 edges. So the degree of a vertex is the number of times an edge touches the vertex. So if I wanted to talk about the degree of Wardlaw, let me look at that vertice Wardlaw. How many times does an edge touch that? Well, there's 4 edges that kind of come out from it. So the degree of this would be 4, because there's 4 edges that touch that vertice. Versus, let's just do one more, the degree of national advocacy. Hold on, my laptop. Ooh, that's ugh. Sorry if that sounded horrendous on your side too. That was my bad. Hello. There we go. And I assume yeah. Okay. Sorry about that. What was I saying? The degree of the National Advocacy Center. So if we look at that vertex, hopefully it didn't cut out too much past when it froze. The degree of this would be 3 because there's 3 edges that touch that vertex. Questions, concerns so far? All right. So let's keep moving. I'll try to keep this in a little bit. There we go. A loop is an edge that connects a vertex to itself. So say we have, whoa. Say we have some, graph, and I'm just drawing these graphs off the top of my head. I'm just pulling out a random graph. And essentially, to pull out a random graph, you can literally just draw a bunch of dots and connect them however you want and call it a day. If I were to do this guy here would be a loop. Kind of almost self-explanatory in a way. So therefore, the degree is not the same. So I should have been careful with my phrasing in the last one. So it's not necessarily the same as the number of edges because a loop would actually be counted twice. So I should have been careful with my phrasing last time. I was saying something like edges coming out of it. If you don't have any loops, it is going to be the same as the amount of edges. But if you have loops, you need to be careful because a loop's actually going to be counted twice. So let me name this vertex A. So then the degree of vertex A in this case would be 1, 2, 3, 4, because it has the 2 kind of regular edges, if you will. But then it has a loop, but that loop's essentially going to be counted twice for how many times it goes in there. So that 3 and 4 isn't counting it as 2 separate edges, but I'm just trying to count how many times an edge touches that vertex. So that loop would actually be counted twice. Even though there's only 3 edges coming out of that, because one of the edges is a loop. So we have 2 different types of graphs. Well, there's a bunch of other different types of graphs, but our next thing is we're going to be able to split up graphs into 2 categories. They can either be well, let me switch back to black. It can be undirected or directed. So an undirected graph is a graph without arrows on the edges. And you'll see what I mean because we'll have the ones with the arrows in just a second. So let me just pull out a random graph here. Let me name these vertices because we're going to want to use that in a second. V2, V3, V3, V4, oh my goodness. V4 and V5, and let me just connect them like this. So that looks like the graphs that we've kind of already looked at. There's no arrows on these edges, but we could add arrows. Well, maybe I should be careful with saying the word add. Sometimes we can be given a graph that has arrows. Maybe I should say it like that. And what that's going to be is that's going to be called something called a, what is my English doing? That's going to be something called a directed graph. So a directed graph is a graph with arrows on the edges. So let me kind of draw that same vertice set, if you will. So I'm kind of starting in the same kind of way. V1, V2, V3, V4, V5. But now my edges are going to have arrows. Oh, okay, that's okay. We can leave it zoomed in like that. So now, essentially, again, not all graphs need context, but say there was context to this problem where maybe it was kind of like the thing we started with where we have buildings and we have roads between them. Maybe all of the roads are one way and you can only go one direction down that road. You can't go the other way. So that's kind of what this would be saying, is that to get from, like, say, vertex 1, you can get to vertex 2, but you can't, well, I need to be careful, but you couldn't go, you know, in this direction to get to vertex 3. You would essentially have to go to vertex 2 and then to vertex 3. You could technically get there, but you would have to kind of go the long way around, if you will. So if we have these arrows on the graphs, it essentially tells us the direction we can travel in, if you will. So sometimes we can't get from one vertex to another if we don't have, you know, an arrow connecting the two. Now, if you wanted to go both ways, usually how that's represented, maybe I should do this. Let me change this one. Instead of doing like a double-sided, you usually have like 2 separate arrows coming out of going from one way and then the other one going the other way. And that would allow you to go in both directions for that one. And then with an undirected graph, you can essentially just go anywhere. I shouldn't say anywhere, but you can go in either direction without needing to care about it. But we're going to use directed graphs for a very specific thing in just a second. So hold on for a second in case people are still writing that down. I don't know why my words aren't working today. All right, so with a directed graph, we don't just necessarily talk about the degree. We have actually 2 different classifications now. We have the in degree. So in a directed graph, the in degree of a vertex is the number of edges coming into that vertex. So essentially how many arrows are pointed at that vertex, if you will. And then we have the out degree of that vertex, which is the number of edges essentially going out from. how many arrows are pointing away from that vertex. So now I kind of have to zoom out again because I want to keep that directed graph in the picture here. There we go. So say I wanted to look up at, well, now I've changed it from my notes, but that's okay, I guess. We look back up at that graph that I have above, the directed one. So let's list the in degrees and the out degrees of these vertices. So if I look at V1, the first vertex over here, well, there's one arrow that's coming. There's essentially what? Excuse me. There's one. Where are you drawing over there? There's one arrow that's pointing essentially to that vertex. So the in degree here would be 1. But then essentially that other edge is the one that's pointing away from it. It's not coming into that vertex, it's going out from that vertex. So the out degree of V1 would be 1 as well. V2 is kind of probably the most interesting vertex on this graph. So how many edges are coming in to this vertex? How many arrows are pointing at that vertex? Well, we have one that's coming from V1 and then kind of that extra one that I drew in there from V5. So our in degree there would be 2. Let me try to erase the circles without erasing everything else. There we go. Then what's the out degree? Well, how many of those edges that are essentially connected to V2 are going out from V2 and pointing to a different vertex? Well, we have the one that's going to V3, the one that's going to V4, and the one that's going to V5. So the out degree there would be 3. V3, third vertex. Yes. So that's actually a good question. So if people don't have the chat up, they asked, do they have to have the arrows for there to be an in degree and an out degree? Yes. So it has to be a directed graph for you to have an in degree or out degree. In a one that's in an undirected graph, the one without the arrows, then it's just degree, because we can't really talk about in or out without kind of this directional idea that we get from the arrows. It's a really good question. So V3, the third vertex, there's one arrow coming out of it that's pointing to V1. So, well, I started with out degree, sorry. So there's one edge that's coming out of V3. So the out degree, excuse you, zoom, would be 1. And there's also only one edge that's coming into V3 from V2. So the in degree would also be 1. For the fourth vertex, there's one edge coming into V4, so the in degree would be 1. And there's no edges going out from V4, so the out degree would be 0, which is okay. And for the fifth vertex, there's one of them coming into it, coming from V2, and there's one going out of it, pointed towards V2. So in this case, both of our in degree and our out degree would be 1. So maybe I'll do a side note to kind of remind us of that answer to that question that I just wrote. So when we talk about degree in general, this is going to be an undirected graph. So no arrows. And then if we want to talk about that type of idea with a directed one, it would be in degree and out degree. Because now we kind of have these directions. Kind of idea. Questions, concerns on that before we move forward? Okay. All right. Okay. So let's see how we're actually going to use one of the kind of contexts we're going to put these directed graphs into, and that's essentially going to be coming back to functions. So functions was part of chapter 2, 2.3, I believe, maybe 2.4, I don't remember. Well, maybe 2.3, because it says recall example 1 in section 2.3. I'm going to remind us what it is, so don't worry if you don't remember what that was. So essentially what happened in that example is we started with essentially a set X that was just made up of 1, 2, and 3. And we kind of drew this mapping between the two sets, and we had this other set, the codomain, which was A, B, C, and D, and E. A, B, C, D, and E. And then how we related them is that 1 essentially went to A, 2 went to B, 3 went to C, and then D and E weren't used. So that was kind of the function we kind of set up in that example way back when. So there's another way we could actually draw this. Let me hold on a second for people who are drawing it. So essentially, now this might seem a little silly, but I can essentially draw the exact same, the exact same thing, essentially just without the circles, which is why it might seem a little silly, but hello, pen. A, B, C, D, and E. And I could say 1 is related to A, 2 is related to B, and 3 is related to C. This is a directed graph. It is perfectly okay that D and E do not have any edges connected to them. I haven't said that yet, but in a graph, you don't need the vertex to have an edge attached to it. So like if I, kind of side note, if I just, draw some random graph and, whatever, I could also have a vertex out here that doesn't have anything attached to it. This is still a graph, even though that vertex kind of off to the side, off to that right side there, doesn't have any edges connected to it. So it's okay that D and E don't have edges coming out of it. Why is that not counting? This is recording. Well, I'm gonna hope that it is working. Anyway, so essentially we could kind of depict these functions as actual directed graphs. So remember, back from chapter 2 with functions, that in order to be a function, every input must have one and only one output. All the outputs don't need to be used. Well, all the codomain elements don't have to be used, like we don't use D and E here. But we would have to have that element that's supposed to be an input must go to one and only one thing. So say we have this directed graph right here. Could this graph be a function? Well, if we think about it, if we're assuming, so it's kind of like if the arrow is coming out of the vertex, you're assuming that it's part of the input set, and then all of the ones that have the arrows pointed to it is kind of the output set. Now it's super nice for this one because they kind of grouped it up for us where all the inputs on the left and all the outputs are on the right. You wouldn't necessarily have to do that in a graph format, and you would just kind of have to pay attention to the direction of the arrows. The thing that the arrow is pointed to would be the output, and the thing that the arrow is coming out of would be the input. So I could kind of scramble these up and it could still considered to be a function. But anyway, so is this a function? Well, if these on the left are all of our inputs, all of those inputs are related to something. If we look a little closer, this input of 2 has 2 edges coming out of it, and that would be bad. I can't have one input going to 2 different things. So this would be no, the input of 2 has 2 different outputs. To go just a tiny step farther, hold on a second.
Is this just another way to talk about like if a function's well defined?
Why is my brain not working? Yes. So yeah, for a function to be well defined, which essentially when we were talking about well defined, that also meant is it actually a function? They were kind of the same thing. So a function is well defined if it has every input has an output and every input only has one output, which is kind of what we're looking for here. Does every input get used and does it only go to one thing? It doesn't go to only one thing here, so it's not a function. It's not well defined. Those are kind of the same thing. To go a tiny step farther, just to hopefully clear up some things maybe, the fact that this 2 in the outputs has 2 arrows going into it is perfectly fine. Remember, multiple things can go to the same output. We just can't have an input going to more than one thing. Also note that that 3 being completely by itself without any arrows going into it at all is also perfectly fine. Again, we don't have to use all the outputs. We just have to use all the inputs. So anyway, that wouldn't represent a function. So if we think about this a bit deeper and about, looking at these directed graphs in terms of functions, what would we need to happen for kind of these things that we were talking about in terms of functions? So how can we know if a graph represents a function? Well, essentially, if I want to phrase this in kind of these graph theory terms that we've been learning, what I could say is I could say every element representing an input, and I'm going to put domain element as well. Can I spell it? Apparently not. Domain has out degree of 1. Because if you think about what that means, now that we know that what out degree means that you have an edge coming out of it, and this would be saying that you only have one edge coming out of it. This would essentially mean that every input has an output because it has an out degree, so it's going to something. So every input has an output and only one output. Oh my goodness. If the out degree is only 1, that means it only goes to one thing. So it goes to something and it's only one thing. So we could also phrase this as this directed graph will be a function if every element that's an input has out degree 1. Well, what about if we wanted to know if these represented one-to-one functions? So if you remember one-to-one functions, one-to-one essentially meant that brain. No inputs go to the same output. So essentially in the graph in example 3, this would not be one-to-one because you have one of the outputs having 2 things going to it. To be one-to-one, essentially all of the outputs can only get mapped to by one thing. So the way we could phrase this in terms of a kind of our new graph theory materials, we could say that the in degree of every codomain vertex. I'm going to put that in quotes. So remember, our codomain is kind of our options of our outputs, our output options. So the in degree of every codomain vertex must be at most 1. It could be 0. One-to-one, it doesn't matter if there are elements that don't get mapped to. So like just in this example 3, that 3 output not having anything to it would be perfectly fine even in a one-to-one function. So it could be 0, but essentially making it at most 1 means that, so essentially it could be 0, but no 2 inputs map to the same output. Because if you had things going to the same output, that would mean that the out degree would be larger than 1. The in degree of that codomain vertex would be more than 1. So if we want these directed graphs to also represent a one-to-one function, we would want all of the in degrees of the codomain vertices to be either 0 or 1, essentially. What about if we wanted these to be onto functions? Now, onto, remember that onto essentially meant that all of the things in the codomain actually got mapped to. Essentially, your range, the things that actually are your outputs, is equal to the possible outputs. So essentially, everything in the codomain would have got mapped to. So if you think about what that would mean in terms of our in degrees or out degrees, is we would want the in degree of every codomain vertex. Must be at least 1. Now in this case, it could be more. But essentially the thing that we care about is that but every element in the codomain is mapped to. So again, one-to-one and onto are completely separate ideas. So like for it to be both, essentially all of the in degrees would have to be exactly 1. But for onto in general, you could have multiple inputs going to the same output. So like in this above example, the only problem that would make it not onto is the fact that this 3 doesn't have anything going into it. If that 3 was mapped to by some element, if this was a function, which it wasn't, but if this was a function, if something was mapping to that 3, then we'd be good to go, even though that 2 has 2 things mapping to it. So with onto, all you care about is essentially every element of the codomain has something going into it. We don't care kind of anything else other than every codomain element gets mapped to. So kind of just relating those two ideas, our idea about functions, to now these ideas of directed graphs. Now again, we're kind of doing this on an introductory level, so we're gonna move on to something else now. We're kind of just building up these definitions of these ideas. But are there any questions, concerns on any of that stuff that we just filled out before I move on to something slightly different? Okie dokie. Okay. Ooh. Now we got to talk about trees. So trees are a very particular type of graph. We'll define it in a second. We'll kind of build up to it in a minute. But it is a graph. It's just a very particular type of graph. So let's say Marie has 2 children, Robert and Ray has no children. Sorry, what am I? Robert and Ray. Robert has no children, but Ray has 3, Allie, Jeffrey, and Michael. Draw a graph to represent these relationships. So this is kind of just thinking back to, like, think about a family tree. If we were to write a family tree here, it would start with Marie. Essentially, Marie has 2 children. So she's got Robert, she's got Ray. Robert doesn't have any more kids, so it kind of stops with him. But then Ray has 3 kids. He's got Allie, Jeffrey, and Michael. So this would kind of be a graph to relate these together. Essentially, relating is one of them a child of the other, the one above it, if you will. So these are going to be connected if the essentially higher level is the parent of the lower level, if you will. This would actually be an example of a tree. And so essentially what trees are is they're a very particular graph that kind of take this kind of shape where it kind of starts really narrow and then kind of expands out as you go downward. So before we get to the idea of a tree, we have to build up a different definition first. So the first thing we need to talk about is something called a path. And hold on for a second. So a path is a sequence of vertices and edges. Now don't let this freak you out. Well, there we go. Essentially what it is you start at a vertex, you tell us what edge you use to get to the second vertex, you tell us what edge you use to get to the third vertex. So in this case, we would kind of have to name the vertices and the edges so we know what we're talking about. But it's essentially just going, you know, on a little adventure through the graph. You're just going from one vertex to the other and you're telling us which edge you're using to get there. So that would be a path, is just essentially a sequence of vertices. So all of our vertices are kind of here, and then we've got to tell them what the edges are that we used to get from one vertex to the other. And that's just the generic notation that I would take. So in this case, when we're looking at this, the E sub i's, the E sub whatever numbers we're looking at, are joining essentially the two vertices on either side of it. So E1 is joining V sub 0 and V sub 1 in this case. So practically speaking, a path is essentially a method to travel from some vertex V sub naught, V0, to V sub n along a series of edges. So it's essentially just how do you get from one edge, one vertice to another along a couple edges. So say, let's scroll down the tiniest bit, there we go. Say we look at that tree that we just wrote down, and I want to get from Marie to Allie with a path. Well, if I start at Marie, I can't just jump down to Allie. I'd have to go to Ray first, and then I'd be able to jump down to Allie. That would be a path. Marie, Ray, Allie would be a path. If we were writing this out in generality, we would want to name those edges, you know, maybe E1 and E2. But when you're also just writing it down in these ways, if you can also just write it like this, I should say. It didn't circle it. There we go. If we want to be formal, then we name the edges, but we can also just kind of say this one jumps, this vertice jumps to this vertice, jumps to this vertice. The only time you really have to be careful with naming the edges is, especially if you're in a directed graph, sometimes you have to be really careful. And there are some other situations where you have to be careful, but they're beyond the scope of what we're talking about right now. So essentially just path is how do you get from one vertex to another one. We're going to say that a path is simple. We'll get to that in a second. We mean that all of the edges are distinct. So essentially you didn't use the same edge again. So in this tree, there's kind of no way to get an unsimple path, but maybe I'll scroll back up in a second. Let me just, when we write it, V sub 0, E sub 1, V sub 1, how do we determine if it is direct or indirect? Yeah. It's not that you would ever just be given a path name and have to determine what, so in case people aren't reading the chat, the question is, when we write it as V sub 0, E sub 1, V sub 1, blah, 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 the notation up here, how do you know if it's a direct or an directed or a not directed graph? And the answer is, you're never going to just be given a string of variables like this and be asked, hey, is this direct or indirect? Directed or not directed. That would never be something that's just asked of you because you wouldn't know. You wouldn't know just being given a string of variables. If you were given the graph, you would look at it. Does it have arrows or not? But if they're just telling you the path in terms of these variables, you don't know whether it's directed or not because there's just really no way to tell because they're just giving you a string of variables. They might tell you when they give it to you, they might say, here, this is from a directed graph, but they would have to give you that information. You wouldn't be able to just magically pull it from just a string of variables. Anyway, hopefully that made sense. Let me scroll up really quick. This one? Yeah, I can probably pull something out on this one. So let me erase these numbers really quick. I don't necessarily need to put them back up because they were just used to count how many we had. But if I want to demonstrate this idea of a simple path, so let me see. Let's say I wanted to go from the War Memorial to, no, let's go from Wordlaw to, oh, this one's going to be gross too. This is just going to seem really silly. Let's go from Wordlaw to LeConte. Now, this is going to seem silly, but just to give you the idea about what a simple path is, I could take a couple paths from Wordlaw to, LeConte. I could go this way and then down. I could go, down this way and across. I could go, straight down, just using the one that's actually connecting the two. Or I could be really, really silly. Maybe I've never been to Columbia before and I don't know where the heck I'm going. And maybe I go up to the War Memorial first and then over the National Advocacy and then down to Williams-Brice and then over this way. But then I go back to the War Memorial and back to the National Advocacy and then down to LeConte. So essentially, I tracked over where I went already. I used those same edges in that path. So since I used the same edge more than once, it wouldn't be a simple path. So essentially a simple path is a path that only uses the edges once. It doesn't have to use all the edges. It just has to, whatever edges you use can only be used once. Let me clean that up. So that's the idea of a simple path, is that you go from one vertex to the other without reusing any edges. Now, of course, you can always take obnoxious paths. You know, I could just circle around that one that I was just looking at for like 5 million years before actually getting to where I want to go. That would be really dumb, but I could. So you can always take really obnoxious paths, but usually we're trying to take the best path, if you will. But again, we're not really talking too much about that. The reason we needed to talk about simple paths is because it's necessary to define a tree. So essentially a tree, wrong color. A tree is a graph with a specified vertex R, which we're going to call the root, with the property that for any vertex in the tree, there's a unique simple path from R to V. Now I'll draw a tree in a second, and I think it makes more sense if you just look at the picture. So in essence, if a tree is a graph with a root and kind of branches, if you will, that's why it's called a tree, because it kind of looks like it starts from one spot and then kind of just trickles down. So it's got a root and branches, and the vertices connected to the root one level down. So you start at the root, you just go one level down. That's going to be its children. That's like the actual thing we call them. Then the same is true for actually any vertex. So you start at a vertex and you go down one level. That's going to be that vertex's children. And going backwards up one level would be that vertex's parent. So I think that example that we started with, with Marie and going down to Ray and Robert and blah, blah, talking about that in the context of parents and children almost makes it extra understandable, because those words are the actual words that we use for a tree. So essentially in the tree that we were just looking at, if you started with Marie and went down one level, those were her children, and they actually were her children, and Marie was actually their parent. But that is the words that we use in any tree, whether it's that context of parent or not. So let me say that I draw some random tree. Let me make it slightly bigger than the other one that we had. This way, this way. Let's just stop there. This would be a tree. So essentially this one here, the top one is the root. And say I name that V. So these two here would be V's children. But then essentially if I go from, this vertex A to this vertex B that I'm naming now, essentially A is B's parent and B is A's child. So essentially it's just, and it only works for like the next one down. Like you wouldn't say, if I have this vertex down here, C, you wouldn't say that C is a child of A, because it's not just directly below it. But that's kind of the relationships between these. And what it means by any simple path is that essentially you can get from one vertex to any other one just by kind of going down the tree in one direction. You don't have to do anything super weird. You don't have to go and repeat edges in any way. You just kind of go straight down and take the direction that you need to go. If you want to go from V to Z down here, you just shoot straight down. If you want to go from V to W that I'm naming now, you almost take a straight shot, but then at the end you just turn off to the side. So essentially between any of these vertices, you can just take a really simple path, which is what makes it a tree. Questions, concerns about that? We're going to get through this whole section today, and that makes me feel really nice. All right, cool. So the main thing you want to pull from these trees, and the main thing that we're going to focus on now for 2.1 and 2.6, is this idea of a binary search tree. Let me leave this up for like 5 more seconds. All right, so a binary search tree. So say, you're typing a thing in Word and it's, you want to use all these silly phrases and you're going to tell it not to count them as misspellings, even though they're not real words. So a custom dictionary is, that spell checker, and you can start telling it that, special words are not to be marked incorrect. So you're going to add these words, kind of one at a time in no particular order. It's just like whenever you stumble across this word that you want to start writing all the time, you're going to add it to the dictionary as it comes. So this custom dictionary idea is actually a special type of tree called a binary search tree. So the term binary means that essentially each vertex can only have at most 2 children. If you think binary code, it's 0s or 1s. You have one choice or the other. You only have 2 choices. So in this example, the left child must come before the parent in alphabetical order, and the right child must come after the parent in alphabetical order. And that's kind of how it makes searching these trees super easy. So what we're going to do is we're going to draw a tree for a custom dictionary with the following obnoxious words: muggle, fleek, snizzle, warfing, fantabulous, and shmushables. All great, amazing words. So what you're going to do now, also, this pops up in your homework a couple times. Usually that they'll add in an extra bit of phrasing. Oh man, I was just looking at these. What does it say? It says something like draw a tree in the order they are given or something like that. Something along those lines. It sounds something like that. So essentially what that means is we're going to take muggle to be the first word that we're working with, and then we're going to continue in the order that we're given these in this list. So here's essentially what's going to happen. That first word that we're given is going to end up being the root. So this guy, muggle, is going to end up being the root, because that's just the first word that we created into this custom dictionary. We're essentially assuming that these are the order that we realized we wanted them to not be marked as incorrect. And essentially what you do is for every next word, you're going to start from the top first. So when we look at the next word, fleek, does fleek come before muggle in the alphabet or after muggle in the alphabet? It comes before, so it would have to be a left child. So we would have to have fleek over here. And then the next word we need to look at is snizzle. Well, again, we have to go back to the top now. So we start with muggle. Is snizzle before or after muggle in the alphabet? Well, it would come afterwards because S is later than M, of course. So we'd have it as a right child. Snizzle. I stole these notes from someone, so I don't know where these words are coming from. I don't know what snizzle is. But anyway. And then if we look at warfing, I don't know what that is either. Again, we have to start from the top. And since this is a binary search tree, we can't have anything more on this level. So this is where we're essentially going to start getting the tree shape now. So it's going to start extending down farther. So we start with muggle. Does warfing go before or after muggle? It goes after muggle. But we can't put it here because snizzle is already here. So is it before or after snizzle? Well, it's after snizzle, so if it's after it, it has to go to the left. That's the right. It has to go to the right. Warfing. Well, now I need to talk about fantabulous. If I take fantabulous, again, start from the beginning. Is it before or after muggle? It's before muggle, so it has to go to the left. I can't put it where fleek is because fleek is already there. So is fantabulous before or after fleek in the alphabet? It would be before, so it has to become a left child. So fantabulous. So in general, this kind of shows us that it's not necessarily going to end up in alphabetical order per se compared to muggle. But it's just kind of based off of the thing above it. Well, I guess if you consider it being this direction, it is still alphabetical order. But anyway. And then our last one is shmushables. So we start with muggle. Is it before or after muggle in the alphabet? It's after, so we would go down to schnizzle. Is it before or after snizzle? It's before snizzle, so this would have to be a left child. So smushables, smushables would go there. Let me think of one more word I want to add in here. I can't think of an obnoxious word off the top of my head though. A, B, C, D, F, G, Q, R, S, T, U, V. Vamp. I don't think that's a word. So say I want to put vamp on there. So if I want to add one more word in here. So again, start at the top, muggle. Is it before or after muggle? It's after. Is it before or after snizzle? It's after. Is it before or after werfing? It would be before werfing, so we'd have to go this way. So this is the idea of a binary search tree. Questions, concerns on that? I think I want to do, we got 15 minutes. I don't think it's worth starting the next page of notes for the next section. So let me just do one more binary search tree just to kind of make sure it's, because this is, it comes up on your homework a lot, so let's do one more. And it's also going to be, now that we've got through it, I'm also going to put it on your quiz. So let's do one more. So say I want to put the following into a binary search tree that says tree in the V order they are given. And let's do numbers this time. So let's say, I don't know, 25, 64, 5, 106, 17, 34, go. And so in this case, we're going to take the left child, essentially a left direction child is going to be less than the number, less than its parent, and a right direction child is going to be greater than its parent. So say I want to put this in a binary search tree. Well, again, this is the order that we're given, so we always start with the first one as the root. So the 25 is going to be our root. And then I look at 64. Well, 64 is greater than 25, so it's going to become essentially a right side child, if you will. Well, then I look at 5. Well, again, I have to start from the top. So 25 versus 5. 5 is less than 25, so it goes to the left. Then I've got 106. Start from the top. 106 is greater than 25, so I head down to the 64 option. 106 is still greater than 64, so that comes off to the right. 17. Start from the top. 17 is less than 25, so we head down to the 5 option. 17 is greater than 5, so we go off to the right. Ooh, this one's a more interesting one. Look at that. Now where I'm at, 34. Again, start from the beginning, 34. Oh, no, wait, this is, it's okay. 34, start from the top. Is it greater than or less than 25? It's greater than 25, so we head down to the 64. 34 compared to 64 is less than, so we head to the left. Yeah, no, wait, this one's not interesting at all. Anyway, and then 2, start from the top. 2 is less than 25, you head down to the 5. Well, I can't use words that I haven't defined. The 5 vertex, and then 2 is still less than 5, so we still head to the left and put a 2 there. So that's actually a very, very nice symmetric tree. But so essentially with these, you always start from the top and kind of, it's almost like those games where, you know, you have to drop the coin in and it kind of just, you know, makes its way down in a weird way. You always got to start from the top and then figure out which direction it should go in until it can have a spot. So it can't take the spot of something that was already there. It has to keep going until it can find its own spot. We still got 15 minutes. Oh. And since we've got so much to cover, maybe I should just do this first example. I think I'm going to. Okay, questions about that though? Questions about any of this?
What is that called again?
A binary search tree. Binary search tree. So again, we're not doing a ton with this right now, but in some of the sections we're about to get into in chapter 3, we need to talk about trees. So we needed to figure out what a tree was. For the last couple of minutes, just so that we don't fall any farther behind than we already are, I'm going to set up the first example for the next section, and then we'll come back to it on Thursday, but at least then it'll kind of be in your brain already, and it'll be, you know, sitting there and stewing for a little bit. So I gotta pull that up really quick. 1 second. I also apologize because I didn't think we would get to this today, so I put up 3-1 just a little bit earlier. So, but again, I'm gonna set up the idea, and that's about as far as we're gonna get. But at least get the tiniest bit into it. That's a good thing. Because after this, so I will say that because I thought it was going to take longer than it did, well, I'm glad it didn't. Your homework for this week is just based off of that graph stuff that we just did. So it's also a little bit shorter than usual. You're welcome. But anyway, so now on Thursday and a little bit of today, let's get into chapter 3. So chapter 3 is all about, well, not all about, it starts off talking about relations. Not exactly as we were talking about them before. So we were talking about equivalence relations, and this is kind of a different type of relation. So we have recurrence relations now. So again, we're just kind of going to set up this idea of example 1, and that's probably as far as we're going to get. But anyway, so you're offered a job for 1 month. Your first option is that you'll get paid $10 million at the end of the month if you work all 31 days. So let's say it's October. And so you have to work all 31 days. And then once you're done working that 31 days, you get $10 million. But if you stop working throughout the month, you get nothing. And your second option is that you could take 1 cent on the first day and quit. Or if you continue to work the next day, you're going to make twice the amount that you made the previous day. And you can keep doing that for as long as you want. You can quit at any time. Which option should you choose? Now, at first, you might just immediately think, well, I can make money in general and then just quit whenever I want on the second one. But like, what if you were really like, I want $10 million? Well, how is the second option going to compare if we went that far? So if we wanted to think about this, if we like started, I gotta draw, duh. If we started to like set up kind of a, oh my goodness, kind of a table here, where we compare our days to essentially the options we have. So option 1 versus option 2. So, you know, we've got days 1, 2, 3, 4, 15, let's say. Whoa, I wrote too big. Gotta scale that down a little bit. 1, 2, 3, 15, 31, and let's even go to a 32nd day. Because option 2 technically doesn't say that you have to work just 31 days. But anyway. So in that first option, for those first 3 days, for the first 30 days, actually, you get nothing. So on the 15th day, you still get nothing. And then on the 31st day, you finally get $10 million. And then if you wanted to work a 32nd day, you would get nothing. What about the second option? So you'd start with a penny. If you came back the next day, well, if you made twice as much as you made there, you would then make 2 pennies that day. And then 4 pennies. And let me put some dots in here to kind of break it up. And then if we keep doing this, we keep doubling. On the 15th day, you would end up making $163.74. And if you keep going up on the 31st day, on the 31st day for option 2, you'd be making $10,737,418.24. So So you'd actually still be making more than you would have had if you just chose option 1. And then if you continued going, then you'd really make bank because you'd be making $21 million. So like, why the heck wouldn't you choose option 2? But anyway. But essentially, we started with this assumption when we're looking at option 2, where the candidate made just 1 penny a day. And then this is essentially what we're going to be calling our base case. So we'll get these first kind of definitions out of the way. And then to figure out how much you made on a certain day, you would have to multiply the previous day's wages by 2. So, you know, we just took the day before, multiplied it by 2, and just kept going. So essentially this idea of taking kind of a value before and multiplying it, or adding or doing something to it to get the next day, if you will, this is the idea behind a recurrence relation. So essentially, if we keep it in terms of this, you know, the example, the wage for day N depended on the wage that you got the day before. Whereas option 1, you just had to work the entire time and it only came into play when you got to 31. So a formula for this function would look something like this. And this is all that this section is going to be about. It's going to be about functions that look like this and have this type of idea of taking the thing before it and doing something to it to get your next thing. So if we think about what this formula is saying, essentially what this is saying is that the first day, when n is 1, so n is the day that you're working. So if n is 1, then you start with 1 cent. That's kind of your starting case. And then for each day after that, you're going to take the amount you made the day before. So this is the day before wages, if you will. And you multiplied it by 2. So we essentially took the thing before it and multiplied it by 2. And what this formula does is actually kind of applied in stages. So when you want to find what W2 is, you actually needed W1. If you want W5, you would have needed W4, and so on and so forth. So we kind of repeatedly use this formula. And so the formula recurs as we calculate values, hence why it's called a recurrence relation. So we'll get this last definition, then I'll stop talking. Well, I might babble a little bit more, but we're going to stop the notes for that part. So we're going to say that this is a recursive definition. I should have made this line longer. Because essentially W is defined in terms of itself. So that's what this section is going to do, and what we'll talk about more on Wednesday. Not Wednesday, Thursday. Is we're going to be having these functions that kind of rely on themselves. They're almost self-referential in a way, where we have to kind of know the lower value, the values for the lower x values, if you will. In this case, they were n values. But anyway, we need to essentially know the before cases before we can keep going. So I couldn't just look at this and say, well, tell me what W of 32 is. Well, if I wanted W of 32, you would have to go backwards. You'd have to find W of 31, then W of 30, then W of 29, then W of 28, and so on and so forth. So these can also get quite tedious if you want to try to get to large values of n in this case. But that's kind of this idea that we're going to work with, is we have a starting spot, and then it tells us what to do with that previous value to keep getting the next one. So we're going to be focusing on this idea of recurrence relations. It's going to lead us up to something called proof by induction. So we're not quite done proofs yet, but we'll get there when we get there. Proof by induction probably won't be until next week, at least, if not the week after. But anyway, now I'm babbling. Your quiz on Thursday. Quiz on Thursday will be written in the chat. Let me put this away really quick. Let me push this over here. So your quiz on Thursday. This is just going to be on the graph stuff. So what kinds of things might I ask you? I might ask you how many vertices or edges does a graph have? I might ask you the in degree or the out degree of a directed graph. So I could also just ask you about the general degree of an undirected. I could also ask you to create a binary search tree. Apparently I can't spell directed or vertices. So those are the ideas that'll pop up on your quiz. Count vertices, edges, count in degrees, out degrees, general degrees, and then binary search trees, which was what we, the thing we had just talked about at the end of T1 and T6, this thing right here. So 3 minutes early, but I think we've done enough for today. So feel free to hang out if you've got any questions. Otherwise, have a good day. I'll see you on Thursday. Yeah.
Hey, could you upload the please?
Yeah, I'll do that right now.
Do you know Dr. Bornstein, Neil Bornstein?
I know him. I don't know him super well, but I know who he is.
Well, last year I had him last semester, and we had the whole COVID thing start, so he kind of had to figure out how to do this like mid-semester. And what he did is he just had one of the overhead projectors like we have in the classroom, and he would just write on a sheet of paper. And at that point, they just let him have one of those at his house.
Oh, that's nice.
But he would just write on that and stream it right over a Zoom call. And he never had any of the issues that you have with lag and stuff like that. So I was going to suggest maybe you ask him, like how he pulled that off, like logistics of it, and see if it might be easier than what you're doing with this program. It might because it might help you not lose time while we're trying to get through the subject.
That's definitely a good idea. I might reach out to him. I know a couple people did some really, really interesting setups for COVID. But yeah, that's a dandy idea, because that's usually what I do in a normal semester is I just use the document camera in class. But anyway. All right, those are up on Blackboard now.
Thank you.